Welcome back to the second lecture on the review of fluid mechanics. In the previous lecture, we looked at the basic equations governing fluid mechanics, in particular the Navier-Stokes equations, and then looked at some simple situations of internal flows, particularly flow through a pipe or a duct. Now we move on to another class of flows known as external flows. External flow is a flow around submerged bodies. And here we have a typical submerged body, an airfoil, which is confronting a free stream, which is the fluid flowing and surrounding it. One of the most important concepts for such flows around submerged bodies, also known as bluff bodies quite often, is the boundary layer around a submerged body. And many of these flows are known as boundary layer flows. Generally, the boundary layer is a small region surrounding the submerged body, and the effects of the presence of the submerged body, particularly the viscous effects, are felt in this small region known as the boundary layer. Whenever there is some sort of flow around a submerged body, a boundary layer will come into existence. Beyond the boundary layer, you have a zone of essentially inviscid flow, in which the viscous effects caused by the boundary layer are negligible, and this flow region gets affected only by the shape of this body. It doesn't get affected by the shear forces which occur on the surface of the body. It is the boundary layer concept which allows us to analyze and visualize the flow situation around submerged bodies. Here I have shown a boundary layer around an airfoil, but there are other situations where you will come across boundary layers of different kinds. One situation is that of a thin flat plate. When it is exposed to a fluid known as the free stream, we expect that, say, on one side the fluid at sufficiently large distance from the surface or a thin plate will remain at V infinity. This is known as the free stream. However, the fluid at the surface of the plate will become stagnant because of the presence of the plate. The fluid will stick to it, and hence you will have a situation where you will have a V infinity away from the surface. The velocity will go down to 0 at the surface. And you will notice that the surface effect is felt only up to a certain distance. Near the leading edge, this effect is much thinner, and as you go away from the leading edge, you find a zone in which the velocity is lower than the free stream velocity, and this layer is known as the boundary layer. On the other side of the thin plate also you will have a symmetric boundary layer. Boundary layer may occur even on bodies such as a cylinder which is exposed to a fluid. Here a thin boundary layer will develop and will grow around the cylinder. Part of the boundary layer may be laminar, part of the boundary layer may be turbulent, and the boundary layer may even separate into what is known as a wake. So here you have part of the regime which is the boundary layer, then we have separation leading to a wake, and depending on the diameter of the cylinder, V infinity, there will be different formats and different forms of the boundary layer and different forms of the wake. As we proceed, we will see some of these situations in more detail. It will be nice to see what exactly is meant by a boundary layer. A boundary layer typically has three characteristics. One characteristic is that it is a thin layer. By thin we mean comparable to the dimensions of the plate. Looking back here, we expect this thickness of the boundary layer to be much smaller than the length of the plate. If the length of the plate is of the order of a meter, the thickness of the boundary layer is likely to be of the order of a millimeter or so. On large bodies like an aircraft wing with a width of maybe a few meters, the boundary layer will be perhaps of the order of a few millimeters or a few centimeters. The second characteristic of a boundary layer is that the component normal to the layer is small compared to the component parallel to the boundary layer. If I show a boundary layer again on a flat plate, let us say this is the boundary layer. In the boundary layer, the component Vx and the component Vy will have magnitude such that Vy is much smaller than Vx. So there is a major and predominant direction of flow along the length of the boundary layer. The component of velocity perpendicular or across the boundary layer will be much smaller than Vx. So here Vy will be much smaller than Vx. The third characteristic is that the gradients of any variable, x component of velocity, y component of velocity, even pressure, along the direction of flow are small compared to across the direction of flow. So for example, if in the same boundary layer I take, say, the velocity profile, this is Vx, so it reduces from V infinity in the free stream to 0 at the wall, and this is the function of y at a particular x, but at a different x, Vx will have different values even at the same y. If you consider the variation of Vx in the y direction, that will be much larger than the variation of Vx in the x direction. Since the gradients of Vx and even pressure, temperature, whatever, are higher in the perpendicular direction than in the flow direction, conduction of heat, diffusion of momentum would all be significant in the y direction, that is across the boundary layer, than along the boundary layer. This is a major characteristic of the boundary layer. So again, remember that the boundary layer has three basic characteristics, that it's a thin layer of flow, thin compared to dimensions of the body surrounding which the boundary layer comes into existence. There is a major velocity component along the direction of the boundary layer. Velocity component across the boundary layer is small, and the gradients are significant across the boundary layer and not along the direction of flow. Now these characteristics, particularly these significant inequalities, simplify the governing equations of fluid flow. That means the Navier-Stokes equations in the boundary layer can be reduced to significantly simplified forms. In particular, the simplification uses the fact that the y component of velocity is much smaller than the x component of velocity, and any component of velocity varies significantly in the y direction compared to its variation in the x direction. The simplified Navier-Stokes equations, simplified using the boundary layer approximations, are known as the boundary layer equations. Here I have shown the boundary layer equations in Cartesian coordinate system, where x is the direction along the boundary layer. So if this is the boundary layer, this is the major direction of flow, this is y. We have Vx and Vy at any point. The continuity equation does not get simplified. It retains its earlier form. Major simplifications occur in the momentum equations. The terms representing the net outflow of momentum, known as the convection terms, they do not undergo any simplification, whereas the terms containing viscous forces are simplified. You will notice that one term which had the second derivative of Vx with respect to x becomes so small that it can be neglected compared to the term containing the second derivative of Vx with respect to y. The momentum equation in the y direction gets so simplified that it reduces to a form where we say that the pressure variation across the boundary layer is 0. This means that the pressure in the boundary layer does not vary across the boundary layer. It will vary in the x direction only. So this implies that pressure is a function only of x and not of x and y. And that is why many times the boundary layer equations are written without this equation and with this partial derivative of pressure with respect to x replaced by the ordinary derivative of pressure with respect to x. In spite of the simplification in the Navier-Stokes equation in the boundary layer, it turns out that these equations are also not so easy to solve. They are easier to solve than the full Navier-Stokes equations, but they are not very simple. So these equations can be solved only for a set of reasonably simple situations. And hence, for most situations of practical interest, and for situation in which the boundary layer is turbulent, either the whole boundary layer is turbulent or the boundary layer is turbulent in part, we use correlations based on experimental data. And just the way experimental data and pressure drop results for internal flows are converted into a dimensionless parameter called the friction factor, here in case of boundary layer flows or external flows, the results are converted into a relation for what is known as the drag coefficient or the skin friction coefficient. We can have a local drag coefficient and the average drag coefficient. The local drag coefficient will depend on the location, so CF at x will be different for different x. Average drag coefficient will be averaged over a certain length. Let us look at the definition of the drag coefficient. If we have a boundary layer, this is the velocity profile in the boundary layer, and because of this gradient of velocity at the wall, this slope represents variation of Vx with respect to y at the wall. There is a shear stress which is equal to mu into this gradient of Vx in the y direction because of the viscous friction due to the finite viscosity of the fluid. And this tau is converted into the dimensionless drag coefficient or skin friction coefficient. As we go along the length of the plate, the boundary layer thickness varies, so the gradient at the wall varies. This will be different at different values of x, hence the shear stress will be different at different values of x, and hence the drag coefficient will be different at different values of x. The local drag coefficient is this local value of the shear stress divided by rho infinity squared by 2, which is the velocity head at V infinity, which is the free stream value of the velocity head. Notice that this has the dimensions of pressure or force per unit area. This also has the dimension of pressure, and hence the skin friction coefficient is a dimensionless number, as is the friction factor, also a dimensionless number. In many practical applications, we are interested in the total drag force, for which we can integrate out the shear force along the length or along the surface and get the value of the drag force. Based on the drag force or drag force per unit area, we can define an average skin friction coefficient. And the definition of the average skin friction coefficient would be the drag force divided by the area of the plate divided by rho V infinity squared by 2. So, maybe I should draw another figure. If this is the plate, and on the plate the total net force because of all the skin frictions is Fd, then take the magnitude of Fd divided by A, where A is the total area of the plate. Force per unit area, this will have the dimensions of pressure, divided by rho V infinity squared by 2, where V infinity is the free stream velocity, and we have our average drag coefficient. And the average drag coefficient can be shown to be, if you have a flow in which the variation is only along the length of the plate, it will be the average of the local skin friction coefficient. Cfx dx integrated over the length and taken average. The flat plate situation, which we have been mentioning again and again, is a basic or fundamental flow situation. The governing Navier-Stokes equations in their boundary layer form can be with some difficulty solved for this situation. And if the flow is laminar, steady, two-dimensional, constant property, incompressible, then we can analytically obtain an expression for the local drag coefficient and the average drag coefficient. It turns out that the local drag coefficient as well as the average drag coefficient is a function only of the Reynolds number. The local drag coefficient is a function of the local Reynolds number. The average drag coefficient is a function of the total or gross Reynolds number. If this is the plate, this is the leading edge of the plate, tau wall at any x is related to Cfx through the local Reynolds number Rex, which is rho v infinity x. X is distance of that position from the leading edge divided by mu. Whereas if you want the total force of drag on the plate over the length L, then for the total force you need the average drag coefficient, and for this you need the Reynolds number based on the length, the total length, which is rho v infinity L by mu. Notice that for a given plate L will be a fixed number, so REL will also be a fixed number, and you will get one value for the drag force. Whereas depending on where you want the local shear stress to be determined, you will have to calculate the local Reynolds number and hence the local drag coefficient Cfx. You will notice that the correlation for the local drag coefficient and the average drag coefficient for the plate are similar to each other, and either of them is inversely proportional to reciprocal of the Reynolds number, either the local Reynolds number or the plate Reynolds number. We have already seen the definitions of the local Reynolds number and the plate Reynolds number. We have seen that the flow in a tube, for example, becomes turbulent when the Reynolds number of flow exceeds 2000, or is turbulent when the Reynolds number is greater than 2000. In case of boundary layers, the situation is a bit different. Again, sketching a boundary layer, let us assume that on this plate there is a boundary layer, and let us say that the free stream is such that it is laminar. There is no turbulence or hardly any turbulence in the free stream. Even then, the boundary layer, which starts off as a laminar boundary layer, tends to become a turbulent boundary layer after a certain distance known as the transition distance. And this transition distance is given by a transition or critical Reynolds number, which for flat plate is 3 into 10 raised to 5. This will be rho v infinity xc by mu. So even though the free stream is laminar, the boundary layer may start off as a laminar boundary layer and then may become a turbulent boundary layer. This transition to turbulence is important and such a situation will arise only if the leading edge of the plate is smooth and sharp. If you make the leading edge rough, ragged, then it is possible to have a turbulent boundary layer right from the leading edge. That is the difference between the tube situation and the boundary layer situation. In a boundary layer situation, under the same condition of a fixed V infinity, it is possible to have a laminar boundary layer first, followed by a turbulent boundary layer. Not only that, by appropriately roughening the leading edge or putting a small extension there, a small spur or a burr, you can make the boundary layer turbulent right from the leading edge. For the laminar part of the boundary layer, we have these analytical solutions. But when the laminar boundary layer becomes turbulent, or for some reason we have a turbulent boundary layer, we cannot obtain an analytical solution. Experimental data indicates that whenever the flow is turbulent, the local Reynolds number is given by an expression similar to the expression for the laminar drag coefficient. This is the local drag coefficient. I have used the subscript TURB indicating that it is for turbulent boundary layer. And here you will notice that it is inversely proportional to Reynolds number raised to 0.2. The local Reynolds number raised to 0.2. This is a correlation based on a large amount of experimental data. We have seen that it is possible to have a boundary layer which is partly laminar and then becomes turbulent. So, if we have a plate in which the whole boundary layer is laminar, we have one situation. But we can also have a situation where the plate is long enough such that the boundary layer is partly laminar, partly turbulent. And we could also have a situation, plate with a rough leading edge, where the whole length of the plate is exposed to a turbulent boundary layer. And we have to be careful while calculating the overall or the average drag coefficient in these situations. If it is purely laminar, we should integrate the laminar correlation. If it is purely turbulent, we should use the turbulent correlation for CFX and integrate it. If it is a combination of the two, we should appropriately take account of the laminar part and the turbulent part. Suppose we have the possibility of the boundary layer being partly laminar and partly turbulent. Then the averaging to obtain the average drag coefficient will have to be done over part of the boundary layer which is laminar using the laminar skin friction equation, and part of the integration to be done over the turbulent part of the boundary layer using the CFX turb, which is the turbulent boundary layer skin friction coefficient. Assuming that XC is less than L, that means we have partly laminar and partly turbulent boundary layer, we get after this integration CF equal to 0.074 REL raised to minus 0.2 minus C1 divided by REL, where C1 is 0 if the boundary layer is turbulent from the leading edge. That means there is no effect of the laminar boundary layer. This is the effect of the laminar boundary layer. And if the transition takes place at REC is 3 into 10 raised to 5, which is an appropriate value, then the value of C1 is 1050. Of course, if we have a boundary layer which is fully laminar, then we should go back to our laminar flow equation and use this correlation. So if we are sure that the boundary layer is fully laminar, we should use this equation. If the boundary layer is partly laminar and partly turbulent, we should use this equation with the value of C1, say 1050. If the boundary layer is fully turbulent right from the leading edge, then well, C1 is 0, so the correlation reduces to only this part. Let us take an illustrative example. We are considering a plate. I will show first a three-dimensional figure. This is the leading edge of the plate. This is the trailing edge of the plate. It is exposed to a fluid. The free stream velocity V infinity is 4 meters per second. And the fluid is air at a temperature of 20 degrees C, but at a pressure of 1.5 atmosphere. In the direction of flow, the length of the plate is 2 meters. The width of the plate is some W, but it is so wide that we don't have to worry about what happens at this edge of the plate and this edge of the plate. What happens at one location is assumed to happen at another location in the width direction. We have to determine what is the average drag coefficient. We have to determine the drag force per unit width or per unit span. We have to determine what type of boundary layer we have, assuming a sharp leading edge, sharp and smooth, and if there is a transition to turbulence, what is the location where the transition takes place. Let us now sketch it neatly. I am looking along the span of the plate. So the width of the plate L is 2 meters. There will be a boundary layer. Let us look at only one side of the plate. The free stream V infinity is 4 meters per second. We measure X from here, and what flows is air at 20 degrees C and 1.5 atmosphere. At this temperature and pressure, if we take properties of air, read them off from a tabulation. Of course, the tabulation will be usually at atmospheric pressure. So you have to note that the density will increase as the pressure increases, but the dynamic viscosity is essentially independent of pressure. So you get mu equal to 18.1 into 10 raised to minus 6 Pascal second, and the density is 1.808 kg per meter cube. We first calculate REL. This is rho V infinity L divided by mu. This is 1.808 into 4 into 2 divided by 18.1 into 10 raised to minus 6, and this turns out to be 7.989 into 10 to the 5. Notice that this is greater than 3 into 10 to the 5. Since our leading edge is smooth and sharp, we expect the boundary layer to begin as a laminar boundary layer, and at some place in between, represented by an XC to be determined, it will become turbulent. So this implies that boundary layer is laminar followed by turbulent. Assuming that critical Reynolds number is 3 into 10 raised to 5, in our correlation C1 will be 1050. So the relation to be used is CF equal to 0.074 REL raised to minus 0.2 minus 1050 divided by REL. If you substitute the numbers, you will get CF equal to 0.00357. And since FD is CF into the area of the plate into half rho V infinity squared. Notice that area is the length of the plate multiplied by whatever its width or span W. Consequently, the drag force per unit width is CF into L into half into rho V infinity squared. If you substitute the numbers, this turns out to be 0.103 Newton. Remember that we have considered only one side of the plate. This is the force because of the skin friction on one side of the plate. If there is a similar boundary layer on the other side of the plate, the total force on the plate because of shear forces on either side will be double this number, which will be 0.206 Newton. Finally, we have to determine, because we have determined that the boundary layer is laminar followed by turbulent, we have to determine the value of XC. And the value of XC can be determined by using the requirement that REC is 3 into 10 raised to 5. And REC is nothing but rho V infinity XC divided by mu, from which, because we know rho V infinity and mu, this gives us XC is 0.751 meters. That means if this is the plate, a total distance of 2 meters from the leading edge, up to 0.75 meters, the boundary layer is laminar, and beyond that the boundary layer is turbulent. So this is laminar boundary layer and this is turbulent boundary layer. After studying the flat plate, which is a basic situation analytically solvable for laminar flow, we go to the other common situation, which is a cylinder in cross flow, a tube in cross flow, a basic situation in external flow. important from fluid flow, important even from heat transfer. Studied extensively, but rather difficult to study analytically. If you take a cylinder and expose it to a stream flowing at the free stream velocity V infinity, depending on the Reynolds number, we get different and very complex flow situations. For very, very low Reynolds number, there is hardly any boundary layer which develops. The flow comes, creeps around the cylinder and leaves. As you go to higher values of Reynolds number, we have a nice boundary layer which develops, laminar boundary layer, which separates. And we have a separation zone, small separation zone here, where there are two eddies counter rotating. At still higher Reynolds number, the boundary layer separates and may also become turbulent. Sometimes the boundary layer becomes turbulent after separation, sometimes it becomes turbulent before separation. So you may have a laminar boundary layer separating and then becoming turbulent, or a laminar boundary layer first becoming turbulent and then separating. When the flow separates and these eddies form, that particular part beyond the separation point is not really a boundary layer. A very interesting situation occurs at higher Reynolds number, where even these separated eddies, they don't remain attached to the cylinder. You have one eddy being discharged or disengaging from the cylinder, another eddy, a third eddy, and so on. Alternatively, an eddy will form on one side and will separate from the cylinder. Another eddy will form on the other side and separate from the cylinder, and so on. This is what is known as the von Karman vortex street, which occurs at reasonably large Reynolds number. And this is a very interesting and complicated flow situation, where you have some sort of a periodic shedding of eddies. In fact, because of this alternate shedding, a lift force which oscillates in the cross stream direction perpendicular to the approaching free stream velocity acts on the cylinder, and if the cylinder is flexible, say a long wire hanging, it will start oscillating, and sometimes you get a nice musical note out of this, a whistling type of note, because this frequency happens to be in the frequencies which we can hear. Each one of these different situations lead to different drag coefficients, and the drag coefficient here, CD, d because it is based on the diameter, is defined as the drag force, which is force in the direction of the approaching velocity, divided by area, divided by rho v infinity squared by 2. One should remember here that unlike the flat plate, where we took the flat plate area, this area is the projected area. Area projected in the direction of flow. So the area will be not pi d into the length of the cylinder, but will simply be d into the length of the cylinder. That is something which we should remember. Because of the variation in the flow pattern, at different Reynolds number, the situation is very complicated for analysis, and except perhaps for very low Reynolds number situation like this, cannot be analytically handled at all. So we have semi-analytic and experimental correlations for CD as a function of Reynolds number. And here we have the correlation which is valid from a Reynolds number as low as 0.1. Below 0.1, the flow situation will be something like this. And as the Reynolds number increases, it moves to something like this, to like this, to like this. And as the flow situation changes, the correlations change. First, you will notice that CD is inversely proportional to roughly 2/3 power of Reynolds number. Then in another range of Reynolds number, CD is proportional to roughly the 4th root of Reynolds number, inversely proportional. Then over a small range of Reynolds number from 1000 to 5000, it remains more or less constant at 1. Beyond that, the CD increases with Reynolds number, roughly Reynolds number to the power 1/8 or so. And beyond that, from 10 raised to 4 to 2 into 10 raised to 5, it can be approximated to a constant value of 1.1. All these different things occur because of the different flow situations that we have analyzed or looked at so far. Let us now take an illustrative example of flow across a cylinder. Here we have a cylinder. The diameter of the cylinder is 75 millimeters. Air flows across the cylinder 60 degrees C, 1 atmosphere. The approaching velocity is 2 meters per second. Cylinder is long at some length L. Naturally, a drag coefficient acts on the cylinder, drag force acts on the cylinder. We have to determine the drag coefficient and then determine the drag force per unit length of the cylinder. We start off by obtaining the properties of air at 60 degrees C and 1 atmosphere. We will need density and we will need viscosity. Any one of the two viscosities will do. The density turns out to be 1.060 kilogram per meter cube. The kinematic viscosity is 18.97 into 10 raised to minus 6 meters squared per second. We first calculate the Reynolds number based on the diameter. This will be V infinity D divided by kinematic viscosity nu. This will be 2.0, diameter 0.075 meter, kinematic viscosity 18.97, 10 raised to minus 6. This turns out to be 7907. So going back to our correlations, we find ourselves in this range, 5000 to 10,000. Ours is something near 8,000, and hence this is the correlation which is to be used for the drag force. So CD turns out to be 0.310 RED raised to 0.1375. Substituting the values, we will get this as 1.065. At high Reynolds number, CD will be roughly equal to 1, between 1 and 1.1. The drag force is CD into projected area, which will be D into L, multiplied by rho V infinity squared by 2. And hence the drag force per unit length of the cylinder will be CD into D into rho V infinity squared by 2. And if you substitute these numbers, you will get this to be 0.169 Newton per meter. So if it's a 10 meter long cable, this will be about 1.7 newtons. This particular illustration shows how to calculate the drag coefficient. In particular, remember that for cylinders, and you will have correlations for a square body or a sphere. These correlations are available in textbooks and in literature. Whenever we have a body except a thin plate which has a significant projected area to the flow, it is the projected area which is used for determining the drag force. It is only for a thin fat plate that we use the actual area of the plate. Now, in these two lectures, we have briefly reviewed fluid mechanics. This was only a review of fluid mechanics. Because it is needed for the study of convection, in which fluid flow and heat transfer go together. We looked at the governing equation, then we looked at internal flows, and then we looked at external flows. We solved some illustrative example to determine the pressure drop and the drag force. Okay. With this review of fluid mechanics, we are now ready to begin the study of convection. We begin with a study of forced convection in the next lecture. Thank you.